Hi everyone, this is again another test utilizing the more powerful rotor. In this configuration here, I'm testing again the dual coils, the same in the previous video, but we were passing the magnets on the side of the coil, and I decided, well, let's try it to see passing the magnets on the front of the coil. So this is basically a standard generator position or coil position, and I'm still getting some very good results utilizing it in this configuration. The voltage won't be as high on the load because I believe basically when we were pulsing with the magnet coming on the side of the coil, we're hitting two coils, and therefore we're getting double the voltage. In this configuration, it's basically one coil, but this coil here in the back is helping to relieve the lens effect like I had found previously. So I think this is encouraging, and I think it should be looked into a bit more and studied, and that's what I'll be doing myself. So there's the connections there, very basic. That's the top coil, that's the bottom coil, that's the bottom coil, that's the top coil. And so basically, to get the effect, you're just having the coils connected in parallel. And this section here, though, I broke this, and this is where the resistor is in between these two coils here, and you can extract the power from there. So I'll start it up and we can look at the numbers. So here are the numbers. We've got again 90 volts, and we're utilizing 800 and about 875 milliamps, and the resistor is not connected. Here I have the other side here, and again I have my voltmeter connected across that 10 ohm resistor. That's the same 10 ohm 1% resistor as we have before. So there's our data, and I'm now connecting. So now the 10 ohm is now connected, and it shoots up, from what I calculate, about 30 milliamps. So look at the data there. I'll give you the scope shot meanwhile here while it stabilizes, and there's the data. So we have a total of 6.38 volts across that load, which is still a cold resistor, so we have an accurate voltage there. And right now, if we look at 900 and about 920 something is about our average. It's now disconnected, and we have about 882 about average. So I can always try my relative position there, but we have to have like a stable 0 to be able to get a correct reading, and as you see, it's kind of difficult to get it. It's varying quite a bit. I might have to use a different kind of motor to be able to get a good reading. So it's kind of stable there, and it's now connected. So it's showing about, yeah, it's going high there, but I figured somewhere around 30 milliamps is the average there. It's now disconnected. So let's do the math on that. We got our 90 volts, about 30 milliamps was the current used. I'll stop the camera right now. So there is the score there. We have, well, I put in 91 volts. We were probably closer to 90 volts. And I put 0.030, which is 30 milliamps. Got a total of 2.73 watts used when the load was connected from the motor. And if we look at our data at the top here, we have 6.38 volts across the load, and again this is previously calculated, and that's our 10 ohm load. We have 4.07 watts. So I think this score here might even be better than the previous test. Anyways, I don't think I could be off that much, even if we increased our bottom here. Instead of using, we can reset that. We can use, well, we had 90 volts, and even if we set it at 0.035 to increase it, we still have 3.15 watts there, and our total up on top, watts out, is 4.17. So even at worst case scenario, we're still 1 watt over on the full total. So I think that's pretty good considering the output and all. So I'll post this video, and we'll continue testing this promising dual coil configuration and post the results. My feeling is maybe the magnets have to be very powerful for the effect to be happening, and it's proving itself. And when I did the original test, I was using some big 2-inch neomagnets. I don't really feel like making something out of that, but who knows, maybe I will in the end. Thanks for watching.